actually. And I invite you to please like stop me at any point. Because I want to go over all the details, I would like for you to be convinced as well. So if there's any detail that you're not convinced of, we can go over it. So let's get started. I'll start with a problem description. So we're given. Yes.
Is there a light just above here?
A light. Oh, this one here.
Some light.
Yeah, you can also see what it does.
Oh, okay. Hopefully this will. Oh, okay. Wow. Wow. Showtime. Okay. So we're given a set of elements.
Is this yours or you want me to do it?
No, that's
This is mine. Yeah, this is for later. Yeah. I do that. Given a set of elements V, and we're given weights on these elements. We'll say W sub E for each element E. And then we're also given, so this is the stochastic part, we're given probabilities. And I should say independent of each other. Independent probabilities P sub E for each element of being active. So every element, it has some weight, let's say non-negative, and it has some probability of being active. And then the goal is to maximize the expected weight of a chosen subset of active elements for S subset of V of active elements. Okay, but you might be wondering now, well, how do we do this? We don't know which elements are active, we just know their probabilities. How do we choose a set of active elements? And this is where the probing part comes in. So probing, in order to find out which elements are active, what our algorithm does is it goes over the elements one by one and it probes them. And when you probe an element, it's like you roll the dice or you draw from this distribution and you find out, okay, is it active or not? Draw the note plus if it's active, minus if it's inactive. And if it's active, well, then we must include it in our set. And if it's inactive, well, we can't include it. So, well, we would just ignore, move on to the next element. Okay, but if this was the whole problem, well, it's very uninteresting because we just have a bunch of elements. They have some probability of being active. It doesn't matter the order in which we probe them. So we look at this one, say it's active, we include it. This one, oh, it's inactive, so we ignore it. This one is active, we include it. And it doesn't matter the order in which we probe them. We would always get the same expected value since all these probabilities are independent. So it's very uninteresting. But to make it interesting, we will add two constraints. So first, we will have a constraint on the sets of elements that we could end up choosing, which I'll denote by V script I in. So script I in is a collection of subsets of V that is downwards closed. So if you have any set in I in, you take a subset, it's still in I in. I'll refer to this as an independent system. And this constrains the set of elements that we can choose. In the paper, they refer to this as the inner packing constraint. So that's where the I in comes from. And we're also going to have a constraint on the sets of elements that we're allowed to probe. So we have another independent system, V script I out, which they call the outer packing constraint. And this is restricting the sets of elements that we can probe at any stage in the algorithm. Set of elements that we probe has to be in script I out. And now it's a much more interesting problem. And you might be wondering now, well, it seems quite theoretical. Like we have, okay, these elements and this probing, these probabilities, like, why are we adding these constraints just to make it interesting? Does this have any sort of applications? As the title suggests, it actually does. And just to give you an example, imagine you're running this online dating app. So you have all of these users And first of all, you have some restrictions on which users could actually be matched to each other based on preferences or whatever. So this would correspond to the inner constraints, constraining the sets of matches you could have. And then the goal of the dating app would be to schedule some dates for these users. Let's say you send these two users on a date, and you could estimate if they go on a date, what's the probability that they end up being compatible with each other? And if they're compatible, well, then they're going to be matched and they're going to leave the app. And if they're not compatible, well, we have to ignore this match and move on to the next one. So sending them on these dates would correspond to this probing instance. And finally, this outer pathing constraint, you could relate this to a sort of user timeout level. Like, let's say this user, you could estimate they have a patience level of 4. If they go on 4 unsuccessful dates, they're going to get frustrated with the app and they're going to delete it. So this would correspond to the outer pathing constraint. So this is one of the applications of this problem. And also the kidney exchange problem has a very similar setup. You could model it in almost the same way. And it also has applications to other stochastic optimization problems, like, for example, stochastic matching that they mentioned in the paper. So plenty of applications, and we can discuss more after. But for now, let us move on to the unweighted case. So the case where all the weights are 1, and we will look at the greedy algorithm. Are there any questions about the setup of the problem? Okay.
Sorry,
Yes, cause
the weights are stochastic.
this.
Weights.
Oh, weights are not. Yeah, thank you. Yeah, weights we know actually in advance. It's just this part. Yes, thank you. Okay. But actually, before we move on to the unweighted case, I just need a couple of definitions. I'm sure you know most of these, but let's just be sure. So the first definition is called the K system. So B script I, some independent system, is a K system. K system if for any subset of the ground set, for any maximal, inclusion-wise maximal subset of X that's independent. So for every subset of X such that S is independent and S is maximal. So maximal in the sense that I can't add any element from X to S and keep its independence. And for every maximum cardinality independent subset of X, so for every T subset of X such that T is independent and T is maximum amongst all subset of X that are independent, I have the following inequality that the size of this maximum independent subset is at most K times the size of this maximal independent subset. So if you think of matroids, matroids would just be a 1 system, since for matroids, this is satisfied with equality with K equals 1 for all pairs or all choices. Matchings in a graph, this would be a 2 system. And if you take the intersection of K matroids, this is an example of a K system. So this is the first definition we'll use. And for the purposes of this, we'll assume that this inner constraint is a K system. And we'll assume that the outer constraints are a K prime system. All right, that's the first definition. Let's look at the next one. So the next definition, I'm sure you've seen this one before, it's just the rank. So given VI again, some independent system, the rank of a subset of the ground set is denoted by R, and it's just the maximum size of an independent subset of X. So max size of I such that I is a subset of X and I is independent, so it's in script I. We could also refer to any I that achieves this value as a basis for X, and then the rank of X would just be the size of any basis for X. Okay, so this is the rank, and then the other definition, or this is the final definition we'll need, the span. So the span of X, so again, with the setup, the span of X would be the set of all elements from the ground set that we could add to X without increasing its rank. So such that the rank of X union E is equal to the rank of X. And this made me think of like a span from linear algebra. If you take a set of vectors, then the span is just all the vectors you can add to the set without increasing the dimension. And this is a similar thing going on here, except it's with the rank instead of with the dimension. So we have these two definitions here. And now I propose the following result, that if this is a K-system, so if Vi is a K-system, then for any subset X of the ground set, the rank of the span of X is at most K times the rank of X. And I'll actually show you the proof because it's very short, but I still found it somewhat interesting, is we take a subset of X that achieves this rank, so such that T is independent and the size of T is the rank of X. And then I claim that this T, which is a basis for X, well, it has to be a maximal independent subset of the span. Well, okay, we'll also note that the span of X always contains X. If we just add an element in X, we won't change the set. So T is a subset of X, so it's a subset of the span, it's independent. Why is it maximal? Well, if it wasn't maximal, we assume for a contradiction that it wasn't a maximal subset of the span, maximal independent subset of the span. So then there exists some E in the span of X such that T union E is still independent. What's the problem with this? Well, E is in the span, so by definition of the span, we would have that, maybe I'll continue it here. The rank of X union E is equal to the rank of X by definition of the span. But then T union E is a subset of X union E. So the rank of X union E has to be at least the rank of T union E. But we assume this was independent, so this is just the size of T plus 1, which is the rank of X plus 1 by our choice of T. But now we get the contradiction that the rank of X is at least rank of X plus 1. So T has to be maximal in the span. But then we just use the definition of a K system to say that the rank of the span of X is at most K times the size of any maximal independent subset. Let's take T, but this is just K times the rank of X by our choice of T. So we get the end of the proof of the claim here. So this is a result that we'll use in the proof of the next stage. Any questions about these definitions or this proof? I think it's fine for now. We probably knew most of this already anyway, so let's move on then. Now we can look at the unweighted case. Yeah. All right, unweighted case. So all of the weights are just one. And then the claim is that if we apply the greedy algorithm to this setup, we get a k plus k prime approximation under these assumptions. So greedy, and I'll explain also how the greedy algorithm works. Greedy algorithm achieves a 1 over k plus k prime approximation to the unweighted stochastic probing problem. And we'll look at a full proof of this. It's based on this LP relaxation that I'll explain in a moment. But before that, I will just explain the greedy algorithm. So it works as follows. We're going to order the elements of our ground set in non-increasing order of their probabilities of being active. So PE1, probability E1 is active, is at least probability E2 is active, all the way up to En. So we're going to order them like this. And then the greedy algorithm is going to go over in this order, and it's going to probe the element whenever it's feasible to do so. What does it mean? It means that at the stage where we're probing E, if Q is our set of currently probed elements, and S is our set of currently chosen elements, then we can probe an element E if and only if, well, first of all, Q union E has to be independent with respect to the outer constraints, but also if E turns out to be active, we must include it. So we also need that S union E is independent with respect to the inner constraints. We can assume that the probability of E being active is strictly positive, because if it's 0, there's no point in probing it. And then if it's strictly positive, there's a chance it could be active, but then we have to include it. So we need these two. So what does it mean to probe whenever feasible? It means these two conditions have to be satisfied. So this is how the greedy algorithm works. And now we'll look at a proof of this, performance guarantee. And we'll note that actually the greedy algorithm, we could summarize it with this directed tree. Because we start with E1, and we're going to say, can we probe E1? Maybe we can't even probe E1, but let's assume we can. Okay, then it's active or it's inactive. And maybe if E1 is active, then we can't probe E2. So I'll denote this by a 0, move on to E3. Oh, but maybe if E1 is inactive, then we can probe E2, and then it's active or inactive. And then maybe in this case, we can probe E3, but in this case, we can't. But in this case, because E2 was also inactive, maybe we can probe E3 here. So we just get this very large exponentially sized tree that represents all the possible outcomes for the greedy algorithm based on whether or not the elements are active. And we'll use this idea in the proof as well. So let's move on to the LP relaxation. So this is the LP relaxation of our problem. It might seem a bit mysterious, like why did we choose this? The reason why we choose this is if we're given some policy for stochastic probing, and we set our y vector for at each element to be the probability that that element is probed by our algorithm, then actually we'll get a feasible solution to this primal. And also the objective value will be the expected value of the policy. And I'll show you a proof of that after we look at this dual part. What we're going to do is for every possible outcome of the greedy algorithm, we're going to give a dual solution which has a certain bound on its objective value. And this will give us a bound on this. And then from what I said before with the going from the policy to a solution to this, we'll complete the proof with the final inequality. So that's the setup for this proof. And yeah, let's get started with that. I'll erase this. And yeah, maybe I should erase the rest of this. maybe, so to prove, we want to show this 1 over k plus k prime approximation. All right, so let's let pi be any outcome of the greedy algorithm. So pi corresponds to just some path down this decision tree, or not even decision tree, but just activation tree. And pi is any outcome, and we're going to define a dual solution as follows. If we let S pi be the set of chosen elements in this outcome, and Q pi be the set of probed elements, and we'll actually explicitly write out what it is. Let's say it's A1 up to AL. Be the set of probed elements. Then we're going to define our dual variables as follows. So we have these alphas and these betas for every subset of the ground set. And I'm going to define as follows. Alpha of the span of S pi is going to be 1. All other alphas 0. And then beta of the span prime. So it's worth mentioning now, we have these two constraints going on. So when I refer to the inner constraint, I'll be using span and R for the rank function. When I refer to the outer constraints, I'll be using span prime and R prime. And if you think of these constraints, this would be for the inner packing constraints, and this would be for the outer packing constraints. Yes, okay. So beta of the span prime of some subset of this from A1 up to AH, A1 up to AH, I'm going to set this to be PAH, so the probability AH is active minus the probability AH plus 1 is active for all H from 1 up to L. And there's some fake value here. There is no element L plus 1. So we're just going to set P of AL plus 1 to be 0. And there's a couple things to note about this. First of all, this is indeed well defined. You might be a bit worried and say, what if two of these spans are equal and we're setting it to be two different things? Well, this actually can't happen because if we take two of these sets, they'll be one will be a strict subset of the other, and they're both independent. So if we look at the span of this set, it can't contain any element from the larger set because it would increase the rank, but the span of the larger set would include it since it has to include every element of itself. So this is indeed well defined. And the next thing to note is that indeed this is non-negative because by the way we consider the elements, AH was considered by the greedy algorithm before AH plus 1. So in this order, therefore its activation probability has to be at least the activation probability of the next. So this is non-negative. All the other beta values will set to 0. So we immediately have non-negativity. Let's compute the objective value of this. Okay. Maybe I'll do it. Maybe I'll do it here. Okay. Is it okay for the camera if I do it here, or maybe I
probably
should
not.
stay here? Okay.
Can you just like move the board?
Oh yeah, that's a good idea. Oh, like this one. Oh, this one here. Oh
Yeah,
yeah,
you can move that one here.
this one here.
That
Oh,
one here,
this
and
one.
then you can-
Oh,
then you
I
can-
see. Yeah.
Is it clear why it's like feasible?
Oh, so we're gonna check
Okay.
feasibility and also the objective value. I just following the order of the paper, they show the objective value, so like why not stick with that? But I guess, yeah, I think it's okay if I just continue here, which is as long as we remember what these are, it should be okay. So I'll just erase.
Okay, maybe don't erase it, but use maybe there are like 4 boards inside there.
Oh yeah.
And you can rearrange it.
Okay. Like move this.
Yeah, like finish writing what you need to write in here, and then
Okay.
maybe use some other boards.
Some other board. Maybe I mean I think this is okay, but I can do it here maybe.
I mean, we can also move the camera to a central spot.
Yeah,
It's okay. I think as long as so that this is the important thing here.
now it's
I could just continue here. Maybe. Okay, what is the objective value? So the first part, the only alpha value that's non-zero is this one. So we would just get the rank of the span. So objective value of this solution with these alphas, these betas, only alpha value non-zero is this one. So rank of the span of S pi times 1 plus the sum. So these are the only beta values that are non-zero. So the sum from h equals 1 to L of the rank prime of the span prime of A1 up to AH times the beta value, which is PAH minus PAH plus 1. But this is where we're going to use that previous claim to say that because the inner constraints are a K system, the rank of the span is at most K times the rank of the set. But this is the set of chosen elements, so it has to be independent, so the rank is just the size. And then here, we're going to use the same inequality. So the outer constraints form a K prime system. So the rank prime of the span prime of A1 through AH, it's at most K prime times the rank prime of this set. Again, it's independent. So since it was probed elements, so it's just H, and then we have PAH minus PAH plus 1. But this part actually simplifies very nicely if we just take out this K prime, and then we look at what this is. This is PA1 minus PA2 plus 2PA2 minus 2PA3. And you could probably see the pattern here. The last one is going to be LPAL minus 0. This gives us PA1. This also gives us PA1. This is also, PA2. This is going to give us PA3. So we just get the sum of all of the probabilities of the elements that were probed. So this sum, so this is K times the size of S pi plus K prime times the sum H equals 1 to L of, let's write it as just the sum over all elements in the set of elements that were probed. So all the elements that were probed, probability that this element is active. So the dual solution has objective value at most this. Now let's show that it's feasible. So I'll just write here, the objective value is at most K times size of S pi plus K prime times the sum over all elements that were probed, the activation probability. All right. Let's check feasibility. So this condition here. So feasibility, we have this constraint for every element. So let's let E be an element. And we're going to consider 3 cases for this element. The first case is that E was probed at some point in this outcome of the greedy algorithm. well then E is just a G for some some G between 1 and L. But then E is in the span prime of all of these sets for all H at least G. So it's in the span prime of A1 up to AH for all H at least G, also H at most L. The reason for this is simply because it's an element of the set, and then the span prime will contain the set. So then if we sum up this left-hand side, let's just ignore the alphas because they're all, this part is not negative, so it'll just help us. Let's just look at these beta values, summing over all sets that contain E. We sum over all subsets that contain E, the beta values. This is at least the sum of the beta values of all of these sets. So this is H equals 1 to L, beta of these sets, which is PAH minus PAH plus 1. Well, with this simplifies very nicely, because this is H equals G to L, because this is for all H at least G. So H equals G to L of this set of these beta values. This is PAG minus PAG plus 1 plus PAG plus 1 minus PAG plus 2. And you can see what's going to happen here. All of these are going to cancel. At the end, we'll have PAL minus 0. So that's also going to cancel. And we're just left with PAG. But the PAG is just PE because of this. So we indeed get that the left-hand side is at least PE. So in this case, we're good. But we have more cases to consider because this is only the case where it was probed. Let's look at the other cases. So we'll actually have two more cases because if E was not probed by the greedy algorithm, there's two reasons why this wouldn't happen. Either we can't probe it because of the outer constraint, or we can't probe it because of the inner constraint. So we'll consider these two cases separately. In the first case, E was not probed because of the outer constraint. What happens here? Well, let's consider the point in the algorithm when E was considered. Let's look at what the set of probed elements was at that point. It was, say, A1 up to AG for some G. This could also be empty, it's possible. But we have some set of probed elements at this point. But then when we add E to this set, it's no longer independent, or that E is in the span prime of this set. And actually, E is in the span prime of any larger set that contains this one that's still independent. It couldn't increase the rank of that either. So E is in the span prime of A1 up to AH for all H at least G. But this is exactly what we had in the previous case. So if we do the same thing, we ignore this part, we look at this part, we sum up these values, we'll again get that the left-hand side of that constraint is at least PAG. But now, PAG was considered before E by the greedy algorithm, so its activation probability has to be at least activation probability of E, so we again get the feasibility. All right, and now the final constraint, or final case, sorry. The final case is that E was not probed by the greedy algorithm because of the inner constraint. And then we get that E has to be in the span of the set of elements that were chosen. Because at the moment when we consider E, the set of chosen elements, which is some subset of this. And then if E was not in the span of S pi, we can add E to S pi and maintain independence. So the subset adding E, we could still maintain independence. So we must have this condition here because it violates the inner constraint. But now if we look at the left-hand side here, before we're ignoring this part, let's ignore this part because it's not negative. And then we get this part, we have a set that contains E, namely this set, and we set its alpha value to 1. So the left-hand side would be at least PE times, okay, sum over all sets containing E alpha of S, but we have this one, so PE is at least PE times alpha of the span of S pi, which we set to 1. So we again get our feasibility in this case, and that completes the proof of feasibility. Any final questions about this part? Seems good. Okay. Well, now we're in a good position because for every outcome of the greedy algorithm, we have this feasible dual solution with this bounded objective value. But we could actually do a bit better than this because we can combine all of these solutions in the following way. If we just take the sum over all possible outcomes pi, the probability that this outcome actually occurs times our greedy solution, so alpha pi, beta pi, defined as follows. Well, this is a feasible dual, and this is a convex combination of feasible duals, so we get another feasible dual. So this is another feasible dual, and let's compute what its objective value will be.
Is this like the average of the leaves of the decision tree?
Average of the leaves of the decision tree.
Because you're gonna have like your decision tree. Yeah.
So yeah, every outcome would be going to a leaf.
Yeah.
And I guess for every leaf we could say what's the probability, and then we're multiplying this probability by
the solution that it used, right?
yeah, exactly. And actually it is going to be related to the expected value, which we'll see here. It will work out very nicely. Yeah, but very interesting there.
The sum is over all the independent sets.
The sum is over all the possible outcomes of the greedy algorithm. So all the possible paths down this decision tree. Just for each one of those paths, we can form this solution. So then we could, this feasible dual, so then we could combine them all like this. And these probabilities have to sum to 1.
But like this has to be more complicated than just the output because of the dependency on the choices, right?
Dependency of the.
I mean, like you cannot fix like this summation that David said, like just from the output, like S and Q, right? Because you could get to the same S and Q like in different ways.
S and Q different ways. Sure, but we would just be combining the same one, and I think that would be fine as well. Yeah. So yeah, I think it's okay. You could get 2 different paths that lead to the same S and Q, and we can still combine them. I believe. Yeah, very interesting points here. But let's see what the objective value of this is. So at each term in the sum, we could use this inequality. So this would be at most sum overall possibilities probability times this. So k times number of elements chosen plus k prime times the sum over all elements that were probed probability. And if we just do some rearranging here in the first part, we distribute this, take out the k's, probability pi size of S pi plus well, continue plus this next part would be K prime times the sum all pi probability of pi times the sum over all elements that are probed probability the activation. Okay. But then if we look at this part here, the sum over all possible outcomes, probability of the outcome times the number of elements chosen, but we're in the unweighted case. So the number of elements chosen is just the value of the greedy algorithm. So this is the expected value of the greedy algorithm. So this is good. But now I have to convince you also that actually this part here, I'll call this star, this is actually also the expected value of the greedy algorithm. And let's see why. So I'll erase this now. Okay. Okay, let's see why this is also the same expected value. So expected value of greedy, sum over all possible outcomes, probability times size of S pi. And I'm going to rewrite this as, instead of writing number of elements chosen, I'll just write it as the characteristic vector for the set of elements chosen. So I'm just going to put a 1 in position E if E was chosen and 0 otherwise, dot product with the all ones vector. And the reason why I did this is just because then I can take this out by linearity here. I can take the dot product out. But then if we think of what this is, sum over all possible outcomes, probability of the outcome times the characteristic vector of that outcome. This is a vector where for each element, it's giving me the probability that this element was chosen by the greedy algorithm. So here we would have the probability that E1 chosen by the greedy algorithm, and so on. So what I'm doing here is I'm just summing all of those probabilities. So here I'm just summing over all elements in V. The probability that E is chosen by our greedy algorithm. But if we think of what this means, how is E chosen by the algorithm? Well, it has to be probed by the algorithm and it has to be active as well. But these events are independent of each other by the setup of the problem. All the activation probabilities are independent, so we could just multiply them. So we would just get, this is the sum over all elements, probability that E is probed by our algorithm times the activation probability. All right, but then I can recombine this in a way to get this. Oh, sorry, I forgot to. Yes, this I can write as the sum over all. The probability that E is probed, I can write as the sum over all possible outcomes that probe this element, probability of the outcome. So let me continue here. Sum over all elements. So probability E is probed, I can say this is the sum over all possible outcomes pi, such that E is probed by this outcome pi, probability of pi. Okay, and then times PE. Oh, but then I could put this in here and do multiplication here. And then I have this sum So I'm summing over all elements, and then, so I'm summing like over all pairs, elements and outcomes that probe that element. I could just do it in the other order and do the sum over all possible outcomes, sum over all elements probed by this outcome, this same expression. Just reversing the order of the summation. But then I can take this out here and I get this. So it works out very nicely. So then star is then equal to the expected value of the algorithm, greedy algorithm. But then this whole expression is k plus k prime times the expected value of the greedy algorithm. Okay, so this is very good because now we have shown that the optimal value of this LP relaxation is at most k plus k prime times the expected value of the greedy algorithm. So it remains to show this part, that the optimal value is at least the expected value of any possible policy that we could imagine. And as I suggested earlier, we're going to do this thing with the y vector. We will construct a feasible y vector that has these probabilities of being probed at each entry, and we'll see why this works out. So I'll erase these. Okay. All right, let's say we're given a probing policy. Even it could be adaptive, non-adaptive. Oh yeah, note also that the greedy algorithm is a non-adaptive policy because it doesn't change based on the outcomes. Given an optimal probing policy POL, we're going to set y star e to be equal to the probability that E is probed by the policy for all E. Okay. And for sure it's non-negative. Why does it satisfy this? So if we take any subset and we sum all of the probabilities, why is this at most the rank with respect to the outer constraints?
You can only probe like if you know it could be on the outer subset.
Yeah, that's exactly the idea. And if we want to, well, one way of showing it, I think, is we can write this as the linear combination. So we can write y star as the sum over all possible outcomes, just like we were doing in the previous case, probability of the outcome times the characteristic vector of the elements that were probed. But then this set is independent with respect to the outer constraint. So when we take the characteristic vector, of course it has to satisfy this, because if it didn't, then we would get some subset of this set that's not independent, which would contradict the downward closed property. But then we get again a convex combination of all of these vectors which satisfy this constraint, so we're good. But what about the second one? The second one, I'm going to define this x star, where x star E will just be the probability that E is chosen by the policy for all E. And then this x star, we can write, oh, well, before we do that, let's think of what x star E is by the same argument as before. what's the probability it's chosen? It's the probability that it's probed and it's active and they're independent. So this is just y star e times PE, which gives us these same ones here. But then x star, we can again write as the convex combination characteristic vector of the elements that were chosen. So again, this would be independent with respect to the inner constraints. So the characteristic vector satisfies this now, and then we get that x star satisfies these, but then entry-wise, x star is the same as this. So this y vector would also satisfy second constraint. Finally, the objective value, and immediately we get the objective value as well. Because the expected value of our policy, as we saw in the previous part, we could write it as the sum over all elements, probability that the element is chosen times, or just sorry, probability the element is chosen, which is x star e. But x star e we just saw was y star e PE. Which is the objective value. Objective value of y star. So for every, if we're given an optimal policy, we can construct this y star whose objective value is equal to the expected value of the policy. So the optimal solution to this has to be at least the expected value of an optimal policy. So then we get this is at most this, and this completes the proof of the k plus k prime approximation. So this is the unweighted case. Are there any questions about that? Yes, Nathan.
So this looks like a really grown-up version of like Kruskal is correct using LP.
Yes,
Right?
yeah, and it's funny you mentioned this because I was gonna mention while I was doing this, I feel like this proof, it has like a 650 flavor to it, like very CO 650.
Yeah.
So yeah.
That makes me wonder, like, can you say like something trivial in the case of like matrix, like it is optional? Like this argument that it gives, because it seems to be more powerful than the greedy algorithm, right?
This argument seems to be more powerful than the greedy algorithm.
And it seems like it works for more things. You're working with an arbitrary case system, not only matrix, right?
Yes, exactly.
Does greedy algorithm on K system give like a K factor approximation? I think there was something like that. Maybe.
Yes, they mentioned something like this, and I guess on this topic, I'll briefly mention the unweighted case and what we could do here. Yeah, I guess just a couple minutes on this. I guess we don't need this anymore either. So the unweighted case. Oh, sorry, the weighted case. This did the unweighted case. Weighted case. What do we do here? So what they do is they consider a more general setup where instead of using the rank functions, they just say you could have any LP relaxation of the constraints as long as this is a convex relaxation that contains the convex hull of all of the independent sets. So they consider this more general setup, and the solution that we gave with this y star, it still works in the general setup because of these convex combination expressions. But the point of considering the more general setup is that there's this thing called a contention resolution scheme, which is a method of rounding a solution to an LP relaxation for an independent system to a feasible solution. And they use these contention resolution schemes. They mentioned that there was a paper that showed that they exist for arbitrary case systems. And then they use this scheme to come up with an algorithm for the weighted case. And the approximation they show here is that if you're given an optimal solution to the LP relaxation, then you could get 1/4 k plus k prime approximation. But now the question is, can we solve this LP relaxation like with an optimal solution in general? And it's not known yet. It can be done for matroids, for knapsacks, and also for their intersections. So in these cases, you could do it. But in general, it's not known, but they do say that in general, you could get, again, a 1 over k plus k prime approximate solution to the LP. So in the general case, they say, well, you could get omega of 1 over k plus k prime squared approximation to the probing problem in the weighted case. And yeah, the algorithm was pretty interesting. I didn't have time to show it. I realized like I was going through the paper, like I wanted to go through this. I thought it was pretty interesting, this unweighted case. But if you want to talk about the weighted case, like please come see me after. I'll show you the CR schemes and the how they get the algorithm. But yeah, other than that, I guess I'll stop here. Thank you so much.
Are there any questions?
Yes, Nathan.
Thank you very much for the talk.
Thank you. Yeah.
Do you have like, is it easy to explain like where the square comes from?
Oh, the square. Oh, yeah. So we get this 1 over 4 k plus k prime. If we have the optimal solution to the LP, then we could get this approximation to the probing problem. But then we could get a max 1 over max k prime, I think it is, approximate solution to the LP. So then it would just be like here. So they just write it as this. Yeah.
So 1 by 4 times k plus k prime is in the weighted case, if you have the solution for the LP.
Yeah, so if you have solution for the LP in the weighted case, then you get this.
So I assume the LP is like for the weighted case, you just replace PYE with PYE WE. And
Exactly.
they consider like a generalization of the gradient.
I could just write it down if you want the LP that they consider in the weighted case. They write it as WEXE, where this XE is YEPE, and they say X is in the LP relaxation of the inner constraints, and Y is in the LP relaxation of the outer constraints. So this is a notation they use for just any valid relaxation of the, it has to contain convex hull of all the independent sets. You have some valid relaxation, and then these are the constraints, and then this is the LP. But in the unweighted case, what we did is, okay, these are 1, and then we just considered a specific relaxation where we use the rank function. And the rank function will work, but you could maybe use something else. I really don't know what you could do, but they just consider this general framework, and you could still, if you have an optimal policy or any policy, if you again set Y star to be probability probe, X star probability that it's chosen, you get a feasible solution whose objective value is the expected value, so that works as well.
I assume that in the greedy algorithm, you order the elements in decreasing order of the PEs times WE.
Oh yeah, I guess yes,
And then you-
that this is what you would do, but they mentioned that this is actually very bad. Like you can
Oh,
get very bad cases for this. And yeah, so yeah, they didn't give a proof on the guarantee of greedy algorithm in the weighted case because apparently it could go very
Oh,
wrong.
interesting.
It sounds like knapsack situation, you know, you try to solve knapsack greedily
Yes,
by like sorting by fraction of like how much you get bells per the knapsack it's and the shown it's kind of into better and I guess it's something.
yes, I think it would be related. Yes, absolutely. Yeah. Let's do. Yeah.
Do they mention that there's like greedy algorithm gives k factor approximation for k system?
Greedy algorithm. Oh, they do mention something along the lines of this when they talk about like for the LP or for the
Like for any like k independent system,
Oh,
does
for-
greedy algorithm give any approximation?
I don't think they mentioned this, yeah, but this would be interesting to see.
It seems like this algorithm is like greedy algorithm on the independent system, which is like I in intersection I out.
I in intersection, right. I guess because there's like 2 sets also happening, like the probe and the active.
Yeah, the probability is like messed things up. Like if all the probabilities are 1,
Yeah, yes,
then isn't it like exactly the same as just doing greedy algorithm on I in intersection I out?
I think, yes, they do mention that if the probabilities are 1, then this is actually, it would be tight. It would be exactly 1 over k plus k prime in this case. And they say that this is actually the greedy algorithm for stochastic matching. If you know what the setup is for that. We could take a look, I'll show, but yeah, it's actually interesting when you set the probabilities to 1, this proves the tightness of the approximation. But apparently it's based on the result from stochastic matching, but maybe you know another way of doing it, so. Yeah.
Do they mention an adaptive policy that could be better than 1 plus k plus k prime?
They don't, that's actually what I found interesting. They don't really mention adaptive policy. They say they just mention at the beginning, like, oh, the adaptivity gap measures the difference, but they never met. So even the algorithm they give for the weighted case is also non-adaptive. And they don't mention, they don't say like, oh, like maybe you could do better.
I see.
They don't mention, yeah. So that's also very interesting. Yeah. But I was thinking something about this. One thing they also mention is that they say that the outer constraints are really needed to make the problem, like to give the problem its richness, it said. So it's thinking, what would be the optimal strategy when you just have inner constraints? So when you just have inner constraints, like you have just these independent sets for this elements you could choose. And would you think like the optimal adaptive policy here would be, we look for the set which has highest expected value.
Yeah, probably.
And then we do, with this set, we do in non-increasing order. And then at every point, if it's in, we keep going. But if it's out, then we could reevaluate and say, okay, now that we know that this is out, then what is the maximum expected value of an independent set that doesn't contain this element that contains the elements we already chose? So maybe that would be an optimal adaptive policy. I think, yeah, I didn't want to present because I don't know, I didn't prove that this was actually optimal in the case where you don't have outer constraints, but I think that this would be the optimal adaptive policy in the case where there's no outer constraints. But it would be interesting to see a proof of this, but I didn't think it. So yeah. Like it was hard to imagine that this wouldn't be.
Yeah, I think
it should work. Yeah, it's a classic. It should work, but we don't know. Yeah. Okay. Anything else? Thank you very much for